Yes, thank you, Mr. Chairman. Is this light really necessary? It really hurts a bit in the eyes, but so I can't really see you. Oh, okay, never mind. So I would like to invite you to a journey to Denmark this time, and we have already yesterday there was a presentation from Antje Orts. I think she's not in the room. Thank you. See in this picture. So the development in Denmark, like 20 years ago already, was from like centralized generation units, which are shown on the left as red blocks, towards a very decentralized. So all the like orange dots you can see, if you can see them, they are combined heat and power plants. So every village in Denmark actually has its own district heating system with a combined heat and power plant, a small gas engine implemented, and loads of wind turbines, of course. So all the blue dots are wind turbines, and there's still a couple of large generation units in there. And like 10 years ago, we had a couple of like blackouts. Let me see, it works. So there's the blackout. The people, not only in Denmark, but especially also in Denmark, having already this high share, oh, that's back, this high share of renewables, they fear that this situation will actually happen more often. And therefore, they planned to go for a redesign. And the question, or the identified targets for this redesign process were to increase the security of supply, basically, because not having like these outages or major blackouts. So and further on, the idea was to get some kind of balancing in the distribution system itself. So having like all these distributed generation, why not using them where they are located? And then as well, one of the necessary things is to know what is actually going on in the system. So maybe similar to the previous speaker, like having some kind of state estimation, but maybe knowing at all what is installed, how much wind turbines are in there. So that's what they didn't really know. So it was approximately half the power installed in Denmark, which was in the distribution system, and they had no controllability, and they didn't really know what was going on there. So that was one of the major targets, and of course, then the question with regard to controlling the system efficiently during emergency situations, and by using the distributed generators. And together with that, also talking about black starting, a very big topic in Germany currently also. Can you actually use distributed generations to bring up the system again in case of a major blackout in the overall power system? And heard about virtual power plants and the definition of virtual power plants. So this might not be academic proof, but the idea was also to control the generators in a kind of virtual power plant. I will show later on what we did understand. So according to these targets, there was this idea born of the cell controller. You can see here a distribution system. In Denmark, we have 150 kV down to 60 kV, and then from 60 to 10 kV, and then, of course, the low voltage level. And so the idea was to get some information, like based also similar again with regard to a state estimation, so on certain nodes to measure what is going on there from the generators at the various transformers. And then in case there is some fault in the overlaying system, shown here with this red mark, that the cell controller would actually take over, open the switch to the overlaying grid, and then start to operate the distribution system autonomously. So this was kind of keeping this this distribution system alive, so 60 kV and below. And when we were thinking about the title of this speech here, I was wondering, should I call it microgrid? Well, this is not a microgrid anymore, but it is like a microgrid being able to run normally in grid parallel operation and as well in island operation. So it's maybe a mini grid, or I don't know, it's definitely a smart grid, what sort of. So, of course, to balance, we need to then shut off load or shut off generation depending on what it's going, and then bring as much generation online as possible, and in order to supply as many customers as possible. So we also have another nice sketch on this animation. So in case there is a So you can see the distribution system on the right, and you see the transmission system on the left, kind of. So if there's an error, then we have the CC that's located here, and then would take over, hopefully, at this now, and then opens the breaker and operates like the PV systems, turbines, CHPs, and so on, autonomously, hopefully providing enough energy for all. So this is the area where we actually then implemented this cell controller. It is located in Denmark, close to Legoland. Maybe one or the other, at least the German guys knows this. Legoland was excluded, so didn't want to face an outage. But otherwise, it is like a 100 MVA transformer included. It was an installed capacity of CHPs, combined heat and power plants of 37 megawatts, and installed wind capacity of 3090 over a maximum load as 61 megawatt. And you can see here, like all the small Gs, these are CHPs, and the wind farms, like here, ranging from like 4 megawatt and the CHP 8.8 megawatts. This is kind of distributed generation. This is test area 1, where we started our tests just to see how it actually acts, this cell controller, and then we emerged on the overall complete system later on. So the concept was that each cell should be regarded as a virtual generator, so not virtual power plant, virtual generator. So it should have really good controllability, so like a normal power station. So we would have a strong monitoring, we would have an active control on it. We would like to have an automatic transition to island. So if there's a fault detected in the overloading system, that there would be an issue, like a signal would be sent, and then it automatically goes into island mode. And then, of course, also black starting of the transmission system. So we need a robust cell controller concept, and in order to integrate all the DG units, and the idea is security of supply, basically. But what's not most important is that that we would wanted to do it just based on software. So no, not adding any further devices. However, this didn't turn out to be working. So we need at least to make some of the CHPs being able to control frequency. They might not necessarily be able to do that. So this was the idea of the redesign of the future Danish electric power system. I will go a little bit faster now to the various functionality levels, like active power control of the wind farms, of the synchronous generators were necessary. Reactive power, we have heard about that also the last 2 days quite a lot. Reactive power control, very important. Then voltage control, at least by some of the synchronous generators. Speed control or frequency control by the synchronous generators. Then controlling the breakers, for example, fast islanding. So the target was to be able to island within 1 second, basically. We didn't quite achieve that. It was 1.2 seconds what we achieved, but we were quite happy with that. And of course, we need to shed generation or load in case there is an unbalance, because normal operation, of course, there were reverse flow situations or inflow situations in this island. And then voltage frequency, power control, of course, synchronizing back to the cell. So as soon as the power system is back, for example, that we resynchronize, that is, and black starting I mentioned earlier. So here, these are typical CHP units you can see, and there's one very major part. So it's besides the chimney, it's this one. Just want to point out, and that's the storage. And what Denmark did, they placed next to their CHP plants already in the early stage, very big storage, thermal storage. So they could actually then operate their CHP plant during the week when there's a lot of power needed, and during the weekend they would then withdraw the thermal power from the storage in order to heat the whole village. And therefore, this gives us a lot of flexibility. So this is very important storage in this type, and it's a cheap storage. So it was very good to have these there. This is the wind turbine, or some wind turbines for 1 megawatt wind turbines from NEG Micon. They're bankrupt in the meantime. But this is, unfortunately, I have to say, is a very old, so type 1 wind turbine. So it's a typical Danish concept. and very little controllability. That's a bit of pity because you can do so much with wind turbines, modern wind turbines, so we couldn't really do a lot there. Even we were not allowed to control the condensers, so the compensators. Never mind. Anyways, we had them inside and had to, this was one of the reasons why we added actually some further assets, a synchronous condenser and a dump load, in order to being able to test the system beforehand in a small area. I showed you the area 1, to being able to show the functionality. So a dump load, like very fast switching, and synchronous condenser for voltage control. So our part as Energy Nautics in this concept, in this project, was the simulations. So we built a very detailed dynamic models, and you can see some simulation results here. So the typical like active power is red, and the green power is the other way around. Red was the reactive power, and green is the active power. And so we had a big exchange here. This was in a 400 kilowatt. This is a small area, 400 kilowatt area. And then we went into island mode. So there's no exchange during this period of 400 seconds or 300 seconds to the overlying grid. And then we came back. So resynchronization. And you can see this in like here, where you have a very stable frequency during grid connection. You can hardly see anything. And then after that, like during this control via the synchronous condenser and the load and the CHPs, of course there were some frequency variations, but we stayed within the allowed limits. There's one peak here, one frequency dip. I want to explain why, because we were actually controlling via the dump load. So this is the active power of the dump load, and we came to one of the limits, so we couldn't go further, therefore the frequency dropped in. Actually, so on the right-hand side, you see the active power, like it was able to control from 0 to 1 per unit, 1 megawatt, and the voltage you can see here, which was controlled by the synchronous condenser. So this was the wind turbine, which was actually very active, like varying from 200 kilowatts up to 700 kilowatts during this period of 500 seconds. And we had some issues here with reactive power, not real issues, but as soon as the wind like picks up, the active power is increasing. We have capacitors banks which are actually automatically switching. You could actually see this also in the simulation model. We have implemented that. So I'm running a bit out of time, but here just also thank you. And here you can see also in terms of reactive power, the answer from the synchronous condenser basically on switching of the capacitor bank. Now let's move on to the measurement results. So this is also this small area one because it's a bit more easy to explain here. So you have two substations basically, and one has a lot of wind turbines and CHPs connected. And we have implemented so-called mini island, where we just connected wind turbines with the dump load. And you could actually see that we could operate like the wind turbine only with the dump load, with using the cell controller, the control structure behind, operate safely for like 300 seconds. Unfortunately, then we achieved the limit of the dump load, so it was more than 1 megawatt produced, and therefore we had a blackout here. But until then, of course, it worked very fine, and we were quite satisfied also with this. Then the second point, island operation, as it is supposed to be. You can actually see here again the situation that the frequency, so the frequency is quite stable in the grid. The black one is the frequency in the grid, and the red one is the frequency then during island mode, and we did not go much further than 50.5 hertz. So here in the beginning there was a big difference of over 1 megawatt, or no, 470 kilowatt was actually the exceeding power, and therefore we got this peak there, and then finally we were able to reconnect safely. So during this period, of course, there was a phase shift between the frequency inside, or the voltage inside, and the voltage outside of the cell. And now coming to the virtual power plant, the virtual generator, we were actually able to show this is now 1 hour, where you can actually then give set points. The yellow part is the set points, and then the cell controller could control the different CHPs to bring up and then follow the set point with all the variations due to load and wind, of course, included. So the achieved test results, we have shown that there's a grid-connected, in-grid-connected virtual generator operation. So it's not virtual power plant, but virtual generator, we called it. Did work very fine. We have shown that an emergency transfer has been able to into island operation and back again. So we've done this several times. So having this island alive for like over an hour and then going back. And also with wind only, it was possible when using the synchronous condenser and the synchronous and the dump load. So from a conclusion, we have shown that there's a utility smart grid concept has been successfully demonstrated, maybe one of the first in this size, to our opinion. We have learned a lot of lessons. I just want to put out two at this point. By adding information and communication technology, in order to get a higher security of supply, you can obviously achieve. However, you always also add new sources of failure. So the existing grid is not that bad, actually. So please be careful with this, in my eyes. Not necessarily always put ICT in, and you solve it, you will also add failure. Secondly, of course, from our perspective, modeling simulations are really powerful tools, especially in these situations for island operation. That's very, very important to use like dynamic simulation models. That's all from my side. Thank you very much.